Stanford University.
I have gotten into the pattern, and I like the pattern of first starting a lecture with a couple of preliminaries. Sometimes they're reminders, sometimes they're new things. By now, I've taught so many things so many times that although I may remember that they're reminders, you may think they're new things. But well, I suppose one of the things we ought to go over really quickly, really quickly, is the harmonic oscillator, and I will do that exceedingly fast. But the other thing I wanted to go over before we begin is the spin of massless particles. The spin of massless particles is a little bit different in some ways than the spin of massive particles. The basic difference is that massless particles can never be brought to rest. They move with the speed of light, and if you slow them down, they still move with the speed of light, and if you slow them down more, they still move with the speed of light. Whereas particles with mass, you can truly slow down and bring them to rest, and that makes a difference in certain properties about spin. Which shall we do first, spin or, well, let's do harmonic oscillator first to get it out of the way very quickly. You know it all. I'm just going to, just to set the notation, mostly to get the notation consistent, I'll just go over it with you again. The energy, or the Lagrangian of a harmonic oscillator, is x dot squared. And then for reasons that, if you go back in your notes about the harmonic oscillators that describe the oscillations of strings, first of all, they had a little index n, which had to do with, remember there were cosines, cosine n sigma. It was the n of that cosine. How many oscillations, over the interval from 0 to pi the string makes. So there are, those x sub n's are the coordinates describing various kinds of oscillations. That was there, and for reasons that have no special depth to them, it turned out there was a 4 in the denominator here. That was the kinetic energy, and then the potential energy. If I want to write the energy, I put a plus sign there. The potential energy was proportional to x squared. Same thing, x sub n squared. It looks like we've, somebody didn't do their, there was an x sub n squared divided also by 4. And then, sitting in front is the square of the frequency of the oscillator. And that was actually just n squared. That's what we got for the energy of the nth mode of oscillation, x dot squared, and it's a harmonic oscillator, kinetic energy plus potential energy. That's the Lagrangian, that's the energy, call it E. The Lagrangian is x dot n squared. You know, I'm going to stop writing n. But remember, I'm talking about x sub n. There's x dot squared minus n squared, x squared over 4. That's Lagrangian. From this, you can work out Lagrange's equations of motion, and you can discover that the oscillator oscillates with frequency n. Okay? Let's next go to the Hamiltonian. We want to do quantum mechanics. The way to go to quantum mechanics is to first construct the Hamiltonian and then do some tricks with it. Let's first construct the Hamiltonian. I'll remind you, oops, this is over 4. Somebody should have corrected me. You all fail. X dot squared over 4. Okay, so what do? The first thing you do, what's the first step in constructing Hamiltonians? The first step is to replace the x dots by the momenta. The momenta p. So if you remember, the derivative of the Lagrangian with respect to the velocity is called the momentum. So in this case, with this particular factor of 4 here, the momentum would be x dot divided by 2. Why? Because when I differentiate with respect to x dot, I get a 2. That cancels a 2 in the denominator, leaves a 2 there. All right? That's the first step. Next step is you rewrite the energy in terms of, instead of x dots, you use p's. So we just have to solve for x dot and plug it in here. What does that give us? That gives us, let's see, x dot squared will be 4p squared divided by 4. So this will be p squared with no 4. And then potential energy doesn't change, plus n squared x squared over 4. And that we now call the Hamiltonian, H. The quantum mechanical Hamiltonian is exactly the same, except that it becomes an operator in the space of states. Okay, now the trick is always the same for harmonic oscillators. Let's just erase all of this. This could have been our starting point right here. You look at this, it's the sum of squares, a squared plus b squared. You write that a squared plus b squared, a squared minus b squared is what? It's a plus b times a minus b. How about a squared plus b squared? That's a plus ib times a minus ib. Work it out, you get an a squared minus I times plus I is plus. So you get plus b squared, and the cross term goes away. So you look at this, it's the sum of squares, and you rewrite it. It's a sum of squares in, what is this term a square of? This term is a square of nx over 2, right? All right, so we write that this is nx over 2 plus ip times nx over 2 minus ip. That's the Hamiltonian. Okay. Next step, you give these two things names, but not quite. First, let's think about the commutation relations between these two. Of course, one of these is essentially the creation operator or the raising operator. The other one is essentially the lowering operator. But we have to figure out which is which and the numerical coefficients in order to make them creation and annihilation operators. I'll just put over here for your, to remind you, the commutation relations between annihilation operators, let's call them A minus, and creation operators A plus. A plus, when it acts, raises the energy by 1 unit. A minus lowers the energy by 1 unit. This commutation relation is just 1. So that's how we identify creation and annihilation operators. They're operators which are complex conjugates of each other. These two are complex conjugates of each other. And their commutation relation is 1. So let's work out the commutation relations between these. And just check if we get 1. We won't get 1. All right? What's the commutation relation between x and p? Do you remember the commutator between x and p? Anybody remember? I'm setting h bar to 1. What else besides h bar? I. Go back and try to remember why that's true. xp minus px is I. All right, now here we have x. We have a commutator of n over 2 minus I times the commutator of x and p. So let's first, first of all, what about the commutator between this and this? That's 0 because anything commutes with itself. Likewise, p with p. The only terms are the cross terms, x with p and p with x. All right, so if we just look at the first term here, or the cross term here, that will give us n over 2. It'll give us a minus I from here. But then the commutator of x with p is plus I. So that gets multiplied by plus I. Altogether makes it just n over 2 so far. That's the commutator of this guy with that one. How about this one with this one? Again, I see an n over 2, I see an I, but now I have the p's and the x's in the opposite order. The result is exactly the same thing, just double it. So this one and this one give you the same thing. It just doubles. All of this just gives us n. Now, I wanted to get 1, but I got n. What do I do with it? I just divide both of these operators by the square root of n. In other words, let's divide each of these by the square root of n. Likewise over here, 1 over the square root of n. And that now eats up this n here. And that's the way to remember it if you're on a desert island and you can't remember what combination of x's and p's are creation and annihilation operators. Compared with over here, this is n. This is 1 now. Okay. If I had my creation and annihilation operators interchanged, I would get -1. So we then identify the annihilation operator A minus is 1 over the square root of n. That means square root of n x over 2 plus I over the square root of n p. And the creation operator is the same thing except with a minus sign. I just do that to remind you. There are creation and annihilation operators. The creation operators increase the energy by 1 unit. And when I say 1 unit, I now mean 1 unit. The frequency of this oscillator is n. Oops. N units, little n units. Which n? Well, it depends on which xn I'm talking about. We can now put back our n's. There's a creation operator and an annihilation operator for each oscillation, for each possible oscillation of the string. And the frequency is n. The frequency, of course, is the amount of energy that's added by exciting the oscillator once. So we can work out then what the energies are, what the energy spectrum is, and do the quantum mechanics of the oscillators. And that's basically the spectrum of these strings. Now, we'll come back to it in a minute. The other thing to remember that I talked about last time was if we're talking about strings in the realistic number of dimensions of space and time, namely 3 dimensions of space, 1 dimension of time, good old ordinary space, and we think about the string moving with a great deal of momentum down the z-axis, then there are really only 2 dimensions of oscillation to take into account. Another time, maybe even later today, I'll talk about the third direction of oscillation and how it's determined by the others. But the independent degrees of freedom are the oscillations in the plane of somebody watching the string going down the z-axis. And so how many oscillations are there altogether? Well, there are oscillations along the x-axis. That one's z. Down that direction is z. All right. Toward you is x. Toward the ceiling is y. The oscillations can occur in the x direction. They can occur in the y direction. So that means that there's another term. I really didn't write the full Hamiltonian here. I should have written plus another term where x is interchanged with y, exactly the same. That means for each frequency, there will be 2 oscillators. The oscillator for oscillations along the x-axis and the oscillations along the y-axis. Let's give them names. Let's call them A for the x-axis and B for the y-axis. Same equations, B minus, B plus equals 1. And same equations here, except we'll substitute for A. We'll put B. And wherever I see x, I will put y. What about q? What about p? Sorry. What about p? Yeah, this piece of x and piece of y, the momentum in the x direction and the momentum in the y direction. I won't bother writing it down. All right, from this equation here, and let us put in the little symbol n here. Also goes here. Let's solve this equation for xn. Here's two equations for, let's think of them as two equations for two unknowns, x and p. How can I solve this to find out what x is in terms of the creation and annihilation operator? This is something we'll use later. I'm not sure we'll use it tonight or not. But what I want to write is the coordinate position of the string in terms of the creation and annihilation operators. That will turn out to be quite useful. So let's do it. This is easy. If I want to isolate x, I want to get rid of p. That's easy. Just add these two equations. This term will cancel. So what do we get? We get a plus a minus, and we should put a little index n here for the nth oscillation. That's equal to n, I think it's just n square root of n. Sorry, n square root of n times xn. Square root of n times xn. Square root. So we simply find the nth coordinate is just the sum of creation and annihilation operators divided by square root of n. Real easy. It's just the square root of n that you got to remember. Now let's, before we leave the harmonic oscillator, let's just remember where these oscillators came from. They came from writing x of sigma. Remember what x of sigma was. Oh, there's another one similar to it. Y sub n is equal to b sub n plus b sub n minus over square root of n. Same thing. Incidentally, as I'm sure most of you have heard, the rumor that string theory doesn't work very well when there are only 3 dimensions of space, and I can confirm that rumor tonight. We need more dimensions. To add more dimensions, we just add more coordinates. Fortunately, now you keep adding coordinates until you run out of coordinates. So that's the reason, incidentally, that string theory is in 26 dimensions. Actually, yeah, okay, never mind. All right, remember what x of sigma was? X of sigma and y of sigma. We have a string moving around in the xy plane, looking at it, moving down the axis. It has ends, and along the string, we invent a parameter called sigma. Sigma goes from 0 to pi. All right, and if we take any point on the string, it's characterized by a sigma. It's the sigmith point, if you like, and it has a particular value of x and y. Here's the xy axes. Each point on the string has a definite location. We call them x of sigma and y of sigma. And we use our freedom to Fourier expand x and y, and we find, right, that this is the sum over n of cosine of n sigma times, let's call it x sub n. And what is x sub n? X sub n is simply the Fourier coefficient of the nth cosine wave in the Fourier expansion of x. And likewise with y. Why did I use cosines and not sines? Anybody remember? The boundary conditions are such that the derivatives of x should vanish at the endpoints. That's the condition that the force at the ends not be so strong enough to cause infinite acceleration. But this is the right way to expand the x's. Likewise with the y's. Summation n, y sub n cosine n sigma. And now we can write these coordinates in terms of creation and annihilation operators. We can write them as the sum over n of a plus of n plus a minus of n over the square root of n times cosine n sigma, and the same thing down here with b's. B sub n, blah, blah, blah. Why is that interesting? Well, the best way to manipulate the quantum mechanics of harmonic oscillators is through the creation and annihilation operators. If you want to find out what a particular operator does to a quantum state, you apply the operator, but if you apply it in the form of creation and annihilation operators, you immediately see what it does. Increases the energy, decreases the energy, and that of course will be very useful. But for the moment, they're just equations that I'm writing down on the blackboard because we'll use them. Okay, I won't go through these again. So if there are questions about them, ask them right now. I don't want you to ask me philosophical questions about the meaning of life.
The x sub n is a function also of sigma?
No, no, no. X sub n's are the Fourier series coefficients. All of the sigma dependence is here. This is the sigma dependence. What do the xn's depend on, though? Time, time. There's time in this infinite momentum frame, which we gave a name to. We called it tau. When I write dots, dots always refer to the time in this non-relativistic analogy, which I didn't call t because I didn't want to confuse it with time in the rest frame, so I called it the last time, I believe I called it tau. That means that every point on the string is not just a function of sigma, it is also a function of tau. It's the xn's which are dependent on tau. Why are they dependent on tau? Because they're oscillators. They oscillate. They vibrate. The xn's vibrate with oscillations. They depend on time. The cosines of sigmas, those are the ones which depend on sigma. Okay. Are there any other questions? Yes.
Two quick questions for you. Aren't those for the creation destruction operators, aren't they reversed? In other words, you get subtracting energy from A plus and...
No, you add energy with A plus, unless some was along the line. I think I got it right. We could check it out, but why do you think you subtract energy? What makes you think so?
Well, I mean, it's a negative. You're decreasing the value
Of what?
of A plus.
Of what?
Of A plus.
How can you see how can you look at that and see which way? You may be right, but how can you look at it and see? I don't think you're right, but I'll check. We'll check in a minute, but let's see.
I think he's thinking of it as a real number instead of as a complex number.
I don't care if it's a real number or a complex number. I still don't see how you could look at it easily and see which one raises the energy and which one lowers the energy.
He's just seeing the minus sign and thinking,
Oh, you're looking at this minus sign? That doesn't tell you. You have to go through the quantum mechanics and you have to check whether the commutation relations give you a 1 or a minus 1. And I think I did that. So no, this minus sign doesn't tell you anything. Well, it tells you something, but not. Okay. Next. And that's purely by way of absolute review. Now what may or may, okay. So how much energy, well, all right, I think I said what I had to say. Next question, next preliminary, the spin of massless and massive particles. How many components, or let's say states, does a system of spin J have? Let's start with spin 0. How many states? 2J+1. Right, 2J plus 1. All right, so spin J has 2J plus 1 states. Spin 0 has 1 state. Spin 1, so spin 0, spin. Okay, spin 0, 1 state. Spin 1, 3 states. Spin 2, 5 states, and so forth. However, massless particles are special. They don't fall into this category. A massless spin 0 state only has 1 state. But a massless spin 1 state has 2 states, not 3. A massless spin 2 state system has 2 states, not 5. A massless spin 3, 2 states. The only one which is the exceptional sort of odd man out is the spin 0, has only 1 state. All others have 2 states. For massless. How do we understand that? How can that be? The question is, how can it be consistent? How can it be consistent? I will tell you what the 2 states are. In every case here, the particle, imagine it moving along a certain axis. For the moment, it could be massless or massive. And let's suppose it's moving along a certain axis. Let me consider the component of spin along that axis. What's the maximum? Let's forget spin 0 here. That only has 1 state. But let's go to spin 1. What's the maximum spin along any given axis? Well, the answer is the spins along any axis can be 1, 0, and minus 1. How about for spin 2? 2, 1, 0, minus 1, and minus 2. Okay. In each case, there is always a maximum spin. In this case, a maximum and a minimum, meaning to say maximum positive and a minimum which would be negative. Okay. Those can be thought of as the states where the spin is maximally along the direction of motion or maximally opposed to the direction of motion. Now, as far as whether the spin is along the direction of motion or against the direction of motion, that's really an arbitrary choice of right-hand versus left-hand rule. Spin has to do with rotation. Momentum is a vector along an axis. My right hand, my fingers curl right-handedly. My left hand, they curl left-handedly. A spin that way is considered positive along the axis, and a spin that way is considered negative along the same axis. Well, simple reflection symmetry tells you if you have one, you better have the other. If you have a right hand and you're in a world with reflection symmetry, you will have a left hand. If there's a right-handed particle that can spin that way, there'll be a left-handed one that can spin the other way. So, if you have a particle moving down the axis with the maximum component of spin, there must be another possibility. The particle must also be capable of having the opposite, namely the minimum component of spin. But is there any reason why it has to have spins in between? So let's take the spin 1 case. The spin 1 case, the 3 states along that axis have spin 1, 0, and minus 1. Those are the 3 states. We see, because of reflection invariance, that if it has a spin 1 along the axis, it must also have a spin minus 1. Must it also have a spin 0? Well, the answer, a z component of spin along that axis. And the answer, as I said, depends on whether the particle is massive or massless. So let me show you why. Supposing the particle is massive to begin with, and supposing it has, let me argue that there must be 3 states that it has. If it's moving down the z-axis, and it has spin along the z-axis, so it's rotating this away. Now imagine bringing that particle to rest, or better yet, moving in such a way that you keep up with the particle. It's not moving with the speed of light, it's got a mass. You keep up with it and you look at the particle, and the particle's at rest. Okay? The particle is at rest, so now you've discovered that there's a particle at rest, but moving along with it doesn't change its spin. If it's rotating this way and going down that axis, and you keep up with it, it will still be rotating that way. So it still has spin 1 along this axis. It has spin 1 along this axis, but now that you've brought it to rest, you can rotate it and then boost it back up. In that case, you've created a particle which is neither spinning about, which is neither has maximal spin in that direction or minimum spin in that direction, but which is now has spin pointing out of the blackboard, even though the particle is moving down that direction. And you did that by, first of all, bringing the particle to rest, and then saying, if you're living in a world with rotation invariance, if there's a particle at rest whose spin is pointing along that axis, it must also be possible to have it pointing along that axis. Another way to think about it is you could imagine, after having brought it to rest, boosting it along the perpendicular axis. Either way, you wind up with a particle whose spin is perpendicular to the axis of motion. And that must be the case, because you can bring a particle to rest and then accelerate it in a perpendicular direction without changing its spin. Okay, so conclusion. If you have a massive particle, it must have all 3 states. Spin along that axis, spin along that axis, and that's not enough. You have to be able to make up spin along the perpendicular axis. On the other hand, if the particle is massless, there is nothing you can do to bring it to rest. Any Lorentz transformation will leave it moving with the speed of light. So you cannot bring it to rest and then rotate out from under the spin and boost it in another direction. The implication is that if particles have 0 mass, then it's perfectly consistent that all they have is maximal spin and minimal spin and nothing in between. That's typically the case. Now you know this in another guise for the photon. What guise is it for the photon? The polarization of light. The polarization of light can be described in a number of ways. It can be described as linear polarization, circular polarization, but if you describe it in terms of circular polarization, incidentally, corresponds to photons, depending on whether the circular polarization is right-handed or left-handed. It corresponds to an assemblage of photons which are either right-hand spinning or left-hand spinning. There are no photons which are not polarized at all. Polarization is always perpendicular to the direction of motion. It's either right-handed or left-handed. Now, what about linear polarization? There's linear polarization, and I'm going to tell you now what linear polarization is. Linear polarization, if you have linear polarization, is not 0 angular momentum along the direction of motion. It's a quantum superposition of the 2 possibilities, circular polarization to the right and circular polarization to the left. What's the difference between saying it's a linear superposition of polarization states and saying it has no angular momentum at all. It has equal probability for being spinning to the right and spinning to the left. So doesn't that mean that it has, on the average, no spin at all? Yes, it does mean that on the average it has no spin. But if you measure the angular momentum of that photon, it will either be right-handed or left-handed. You will never measure a photon which has no angular momentum along that direction. So there are only two states of the photon. And one other point, let's go back to linear polarization. A photon moving down an axis can be polarized. Here's the plane perpendicular to the motion of the photon. If you send it through a plane polarizer, it can be polarized, let's say, along the y-axis, or it can be polarized along the x-axis. The polarization is a vector, but it's a vector which is always perpendicular to the direction of motion of the photon. It's always perpendicular, and the words for that are the polarization is always transverse. There is no polarization of the photon where the electric field arrow points along the direction of the photon. That's not allowed by Maxwell's equations. Maxwell's equations tell you the electric and magnetic field, and therefore the polarization of the photon, are perpendicular to the direction of motion. So you can have two states of two different polarizations. You could call it the X polarization state of the photon, or you could call it the Y polarization state of the photon. Neither of them is circular polarization. What about circular polarization? Circular polarization is a linear superposition, a quantum mechanical linear superposition, right-handed. Let's call it right-hand polarization, which means spin right-handed. That's equal to the state X plus I times the state Y. No, I won't say it. Left-handed is X minus IY.
Is it the same like with silver polarization, like the Stern-Grolish experiment? If you send I not silver, is it the same type of explanation for?
No, it doesn't have anything to do with, well, it's just circular polarization. Just circular polarization. Just pure circular polarization. Circular polarization is a quantum linear for each photon, a circularly polarized photon is a quantum superposition of a X-polarized photon and a Y-polarized photon. Let me ask this. Supposing I didn't put the I here. Supposing I just considered X plus Y. What kind of photon would that be? That would be linearly polarized, but at a 45-degree angle to the axes. Okay? So, if all you are allowed to do is put real numbers here, you would make linear polarization which could point in any direction perpendicular to the direction of motion of the photon. But having eyes available gives you something new. It gives you circular polarization. If you use as your basis of states the circularly polarized states instead of the linearly polarized states, there are only two of them. So the angular momentum of the photon is either along the axis or along the opposite to the axis, and there is no photon which has zero angular momentum along the axis. The same is true of gravitons, slightly differently. Gravitons are spin 2 objects. If they were massive, they would have 5 states, but gravitons only have 2 states. They, roughly speaking, and this is an analogy I want you to keep in mind. It's a good analogy, and we'll draw on it. A graviton moving down the axis with maximal angular momentum, that means 2 units of angular momentum moving along the z-axis, is mathematically the same as 2 photons, each with 1 unit of angular momentum. Imagine taking two photons, sticking them together, letting them move down the axis. The angular momentum of the two of them, there could be various possibilities. They could both be circulating in the right-handed sense. Then the angular momentum would be 2 units. They could be both circulating to the left. The angular momentum would be minus 2 units. What you don't have is a graviton which corresponds to a photon of right polarization and left polarization. Gravitons have only 2 states, maximal rotation in one direction, maximal rotation in the other direction, and mathematically you can think of just having a pair of photons of right-handed. You can multiply this by another photon of the same kind and think of it as a graviton. That would be useful, a useful way to think about spin 2 by combining 2 spin 1s. What's that?
Can we use this analogy only for spin, 1 graviton, 2 photons, or can we do this with other quantum numbers?
Well, there's a whole field of study which studies Feynman diagrams for gravitons by thinking of them as, roughly speaking, squares of Feynman diagrams for spin 1 particles. But mostly I think it's trickery. There's no real sense in which a graviton is 2 photons. It's just for combining the spins that it's useful. I can't think of any other sense in which it's particularly useful. There are no other quantum numbers. What other quantum numbers does a photon have? Or a graviton? Doesn't have anything else. Has momentum. Has momentum, has energy, and has spin. So, doesn't have charge, doesn't have baryon number, doesn't have anything else.
Well, it doesn't have a jump in the spectrum either, so
What doesn't have a jump in the spectrum?
photon has a continuous spectrum, right? Potentially?
A photon of a given momentum only has one value of the energy.
Right, but you were saying that a continuous spectrum is what distinguishes something that is a particle from something that's not.
Continuous spectrum of rest masses. Or, if you like, a continuous spectrum for a given momentum. The pot of particles with, in moving inside, not a pot, but in a container of some sort, it doesn't really have continuous spectrum, but it has extremely dense spectrum. But what I mean by that is if the entire pot is at rest, there are lots and lots of energy levels. Okay? Certainly we can generate a continuous spectrum just by moving it, but I was speaking about the pot at rest. Now photons, it's true, can't be at rest, so you can't quite use that definition. You use a different definition, say for a given momentum. Okay. So now we know something about harmonic oscillators, we know something about spin. And what I want to come to now is the spectrum of strings, the low-lying spectrum of strings. The low-lying spectrum means the first few states. Let's just remember that energy, in this formal analogy between non-relativistic physics and relativistic physics, energy becomes not mc squared, not the mass, but the square of the mass. So when we speak about the energy of a vibrating string, and we add them all up to find the total energy of the vibrating string, it corresponds to the square of the mass, okay? Not the mass itself. That's just something to remember. Okay, what are the discrete energy levels of the string? And we're talking a string at rest, meaning to say it's not moving in the perpendicular direction at all. What are the energies? Well, we just say, look, it's just a collection of harmonic oscillators. Let's see what we can make. The first state and the lowest state is the state which is annihilated. That's the ground state. by all the annihilation operators. In other words, it's just the state, the ground state. All the B's and all the A's, all the annihilation operators give 0. It's the state in which neither or none of these oscillators are at all excited. What's the energy of that state? Well, if we were doing ordinary quantum mechanical harmonic oscillators, we might say it's a half h bar omega, right? That's the ground state energy of a string. But let's leave it open for a minute. Let's not prejudice the answer. Let's leave it flexible for a moment and call the mass squared. Now what does this stand for? This does not stand for the vacuum. It is not empty space. It is the unexcited oscillators. It's a particle. It's a particle moving down the z-axis, but it's in the ground state of all of its oscillations. I wouldn't say it has no oscillations, because every harmonic oscillator has 0-point oscillations. Because of the uncertainty principle, there's some fluctuation. But every one of the oscillators as quiet as it can be, consistent with quantum mechanics. So this thing is a particle, and I'm not going to begin by prejudicing about what the mass of that particle is. I'm just going to call it m0 squared, whatever it happens to be. This is the energy of the ground state, or the square of the mass of the ground state. And we don't know what it is yet. We don't have a tool yet for finding out what it is. But whatever it is, when we excite it, we will increase it by integer amounts of energy. So let's see how we can excite it, what the lowest energy excitation is. What's the cheapest thing in energy we can do to it? And the cheapest thing in energy that we can do to it is to apply the creation operators, the raising operators, but the lowest one, A1. Remember, each oscillator increases the energy by in units. And so, if we want to consider the lowest energy, we want to hit it with the oscillator of smallest frequency. The oscillator of smallest frequency corresponds to n equals 1. So we hit it with A sub 1. What's the energy of that state? Oh, incidentally, what is the energy of that state? We've increased it by 1 unit. This 1 here indicates that the frequency of that particular oscillator is 1 unit. The energy that you add is 1 unit. This has increased the energy of the ground state by 1 unit. So the energy of this state is whatever m0 squared is plus 1. Nobody's asking me about units. How could I be talking about energy and saying 1 unit, one unit, 1 joule, 1 horsepower, not horsepower, horsepower is power, horsepower second. What's the British unit of, a British thermal unit, yeah. Maybe it's 1 British thermal unit. No, that seems pretty unlikely, doesn't it? So what is this 1? What am I talking about when I say 1? It's something we better come back to. We better come back to units. I hope by the end of the evening we'll come back to units. But in some units, in some appropriate units, the units that we've been working, the first excited state, which is A dagger 1, gives us 1 extra unit of energy. Now, that's not the only state that has 1 extra unit of energy. Is there another one you can think of? B1. Same energy. What about any linear combination of them? If you take 2 eigenvectors of the energy and you superpose them, it gives you back another eigenvector with the same energy. Okay? So any linear combination of these has the same energy. Now, what are the properties of these objects A and B? In particular, I mean, what are their transformation properties when you rotate the space? We have an axis, a preferred axis. I've defined the preferred axis. I have to boost the system up so that it's moving like hell along the z-axis. But I still have a rotation symmetry of the entire thing about the axis that I boosted things. How do A and B transform under those rotations? Well, you ask where they came from. They came from x and y. We wrote that x was some sum involving b's, and no, sorry, a's, and y was some sum involving b's. What is x and y? X and y are components of a vector. That's what they are. They're components of a vector. They transform the components, x and y transform like the components of a two-dimensional vector. What about the a's? The a's obviously also transform as a vector. A and B, if you were to rotate the coordinates, would transform into some A cosine theta plus B sine theta. It would just rotate like a two-dimensional vector. So these A's and B's are vectors. That means that you can consider these two things to have a vectorial character. This one is pointing, they're always in the plane perpendicular to the motion, always in the plane perpendicular to the motion, which is large. This one has some kind of vectorial property in the one direction. This one has vectorial property in the two direction. So these two states transform into each other as vectors. They have the same properties as the plane polarization of photons. The photon polarization is also a vector, namely it corresponds to the direction of the electric field at some instant. It's a vector. It points in the direction perpendicular to the motion of the photon. And so it's looking as if these two things must correspond somehow to a vector character to the particle. Can we turn it into a circular polarization? Yes, we can turn it into a circular polarization. Instead of taking A1 or B1, we take A1 plus IB1. And that's a circularly polarized something. It's a string which has the properties of a circularly polarized particle. And of course, we can put minus there. And the mathematics of it is identical to the mathematics of the polarization states of a particle moving down the axis. They transform into each other in the rotations. We could linearly superpose these with real coefficients, and then we would just be rotating the direction of oscillation. Or we can add them with an I, and we turn them into circularly polarized. Now, this is not easy to visualize. Don't try to visualize it. It's the transformation properties which count. Notice that there is not a third state with the same energy. There is no other third oscillator. There's only the X oscillator, the Y oscillator, and that's it. There is no third state. So there is no third polarization state. There's only one conclusion which is consistent with Lorentz invariance, with relativity, with the properties of these things. This object, these two objects, must be massless. They must be like the massless photon. If there are only two polarization states, That would not be consistent with a massive particle, because a massive particle you can bring to rest and turn its direction of motion and create the third polarization state. So these two things, these two states, behave exactly like the two polarization states of the photon. And moving down the axis, let's not give them any motion perpendicular to the axis, no overall motion. Moving down the axis, and there are two polarization states. They do have the properties of the polarization states of photons, a vector character to them in the perpendicular direction. In other words, they're transversely polarized things. They are identified as photon-like objects in string theory. And they must be massless. If they're not massless, there's something deeply wrong. Lorentz invariance cannot be maintained. And so we come, you must realize by now we've come to a disaster. We've come to a very unfortunate crash where at this point we should throw away string theory. Why? Because m0 squared plus 1 has to be 0. The mass of this object, which is not the ground state, it's been excited by one unit, that's this. If it's to make sense as a relativistic object, it has to be massless, and that means m0 squared is negative. Okay, big deal. Who cares if m0 squared is negative? The problem with that is m0 squared was the energy or the mass squared of the ground state without these A1s. In other words, the string which was not vibrating along the x or y axis, the ground state of the string. That's intolerable. Having a particle with negative mass squared is crazy. Mass squared is positive. How can mass squared be negative? You're going to have an imaginary mass, right? Okay. Rotate what by 90 degrees? And in what space? Negative mass squared is a bad thing. Okay.
Imaginary.
Negative mass squared, imaginary mass, is a bad thing. So let me tell you, say, why is it a bad thing? So what? You've discovered something that a certain parameter is negative. What does it mean? All right. An object with negative mass squared has a name. You know the name? A tachyon. A tachyon. The tachy comes from the same, it's not that it's a tacky particle. I mean, that's not the point. It is tacky, but what's the thing in your car which tells you how fast the engine is going? Tachyometer? Yeah. Tachy is either, I guess it's a Greek word? Tachometer. Yeah, but tachy I think refers to speed. Speed. I think it's a word for speed. And what's that? No, I don't think so. I don't think so. I think it could be linear speed too. I don't know. I don't know my Greek, and I don't even know if it's a Greek word. Maybe it's a Yiddish word. I don't know, but it does. But I think the prefix tachy refers to speed in general. I don't know for sure. But I do know why they called it a tachyon. A tachyon meant that it moves very fast. In fact, so fast that it moves faster than the speed of light. Now, that's clearly something bad, okay? Einstein told us there are nothing that can move faster than the speed of light. So we seem to have encountered something which is a tachyon with negative mass squared. Let me tell, maybe I should stop at this point and tell you a little bit about tachyons. They're bad. We want to get rid of them. They're intolerable. And if every string theory had a tachyon, you would not have heard of string theory. It would have been abandoned sometime around 1969, and you would never have heard about it again. So, of course, the answer is that there are many string theories, many good string theories, that do not have the tachyon. Okay? There are no string theories that don't have this photon-like object. This is a good thing because the world has photons and it doesn't have tachyons. But let me just tell you about tachyons a little bit and how physicists use the terminology today. Only crackpots think that they move faster than the speed of light. Okay? So don't fall into that trap. Or that they can somehow send signals faster than the speed of light. That's not the issue here. But let me show you why there was some idea that they exceeded the speed of light. The important quantity of interest for the moment now is the frequency of a wave versus its wave number. What is the frequency of a, for a or which is equivalent, of course, it's of course equivalent to the energy of an object. Apart from a factor of h bar, it's the same as the energy as a function of the momentum. So let's write that down for an ordinary non-relativistic particle. E of p is p squared over 2m, right? I'll just point something out to you. We could prove something about this, but the derivative of E with respect to P, what is that? P over m. And P over m is the velocity. That's a general rule. It's actually a property of waves. If instead of E you put omega and instead of P you put k, then it's a property of waves that the group velocity is given by the derivative of the frequency with respect to the wave number or the energy with respect to the momentum. Let's try it out for something else. How about in relativity? What's E versus P? Let's start with a photon. Is it E equals P times C or E equals P over C? P times C, right? Yeah. E is equal to P times C. What is the derivative of E with respect to P? Which is, of course, the velocity of a photon. All right? Let's try it a little more generally. E equals the square root of P squared plus m squared. Okay, now it gets a little hard. Derivative of E with respect to P. That gives us 1 divided by twice the square root of P squared plus m squared. And then what's in the numerator? 2P? Okay, so it's P over P squared plus m squared. Sorry, P over P squared plus m squared. Okay, I'm not going to try to convince you that this is the velocity of a relativistic particle, but it does have one property. Notice that it's less than 1. Square root of P squared plus m squared is bigger than P. Okay. Square root of P squared plus m squared is bigger than the square root of just P squared. So P divided by this is always less than 1. That's another way of seeing that relativistic particles always move with speed less than the speed of light. What if there was a minus here? It goes faster than the speed of light. That's why people call these things tachyons. When somebody or other, and I have no idea who it was, first decided that it might be interesting to think about particles that move faster than the speed of light, they postulated a negative mass squared. Okay? The question is, what is really wrong with that? Other than it seems to contradict something that, Einstein taught us. What does a tachyon really mean? And the answer is it doesn't mean something moving or that transmits signals faster than the speed of light. It means that the vacuum is unstable. It means that something can happen that can destabilize the system. That's the usual source of tachyons. So I'm going to give you an example, but first, let's think about wave equations. Let's start with wave equations. These equations are also ways of thinking about wave equations. Here's a wave equation. That's an ordinary wave equation for as a function. Let's read it this way. Okay. What kind of wave is that? What does it move with? Speed of what? d by dt squared stands for omega squared, right? We've done this before. We've done this many times. If you have a wave, the time derivative, each time derivative gives you a factor of omega. What about each space derivative? K, right? Each space derivative gives you a K. So this equation says that omega squared equals K squared, or omega equals K. I've left out the speed of light. I've set the speed of light equal to 1. So what's the velocity of this wave? The omega decay, 1. Okay. How do I turn it into something that moves slower than the speed of light? What do I add? If I want to add a mass term, here it is. We have, yeah. Which side? Can you figure that out? Is it this way? No, it's minus this way. It's minus m squared phi. Then we would have, incidentally, is the derivative with respect to t, is that omega or I omega? I omega, right? If we have something that goes as e to the I omega t and we differentiate it, it gives us an I omega. So this gives us, this is really another way of talking about minus omega squared, this is minus k squared, and this is minus m squared, right? Which is the same as omega squared equals k squared plus m squared, this one here. So this is what you do to, what does this correspond to in the energy? You remember what it corresponds to in the energy of the wave? The energy of the wave has d phi by dt squared, 1/2. It has plus d phi by dx squared. And this gives us plus m squared phi squared. Does anybody remember this from last quarter? Wave equations and the mass term, how you put in a mass for a particle in terms of the wave equations, Klein-Gordon equations with mass. This was the rule. Now notice that, imagine, what is it? This is a kind of potential energy for the field. Notice that it's positive. It's positive if the mass is positive. That means that if you increase phi, the energy increases. The result of that is if you increase phi, it will oscillate back. It's just like a harmonic oscillator. A positive energy when you displace the field a little bit. And because you gain some energy, or it costs some energy, because it costs some potential energy to increase phi, it'll swing back, and the wave will oscillate. What would happen if you had a negative term here, so that the potential energy of phi looked like that? You fall off the cliff. You fall off the cliff. You know. So it's an instability. It's an instability of the vacuum. If you thought that the vacuum was just phi equals 0, and you gave it a little push, down you would go. Here's a kind of interesting question. Supposing you really did start with phi very carefully balanced at the top of the potential everywheres. Everywheres in space, phi was absolutely balanced at the top. Well, it would sit that way forever if it were absolutely balanced. It would be like a sharp pencil, perfectly balanced. You give it a push, the tiniest push, and off it goes. But supposing you pushed it only at one point, right? You want a model for this? I tell you, can we make a model for it? Yeah, I can make a model for it. Here's a model for it to think about. You'll have a bunch of vertical pendulums, and they're coupled together by springs. They're in a gravitational field. If you set them all up perfectly vertically, they will stay that way. If you only had a single pendulum and you gave it a little push, what would happen? In fact, it wouldn't fly off to infinity, but it would make a big deviation from where it started. So the starting point was unstable. What happens if you push all of them simultaneously? Well, you know what happens. They all go flying over the top. But here's an interesting question. Supposing you pushed one of them, only one of them, this one right over here, how fast would the signal propagate outward? You push one of them, it pushes the next one, it pushes the next one, and sure enough, if you wait, they all go flopping over. But how fast does that signal spread out?
Made a sound, which is story.
Well, we're thinking about light being the velocity of waves. Does it go faster than the speed of light, the way the tachyon suggests it might? Doesn't. It doesn't. The falling over, the domino effect proceeds with the edge or the outer boundary, the outer envelope of the domino effect will spread out no faster than the speed of light. So the conclusion is that tachyons are not to be thought of as things that go faster than the speed of light. String theory has not provided a way of exceeding the speed of light. What it's done is it's given us a theory with an unstable vacuum. A little tiny push will destabilize the whole world. That's not a good thing. That's something that we need to avoid. And that's where superstring theory comes in. That's why we need it. That's why we have to do better than just this very simple string theory that I've described. But okay, so far what we found, if we ignore the tachyon, just say somehow by magic we're going to get rid of it, we have found a theory which has a photon-like object in it. A massless photon-like object with two polarization states, and it's a candidate for something like the photon. I said to you that there are tricks and ways of getting rid of the tachyon. You might ask me, are there tricks and ways of getting rid of the photon-like object, the massless thing? Well, the answer is nobody ever found one. Within months of the discovery of string theory, people had figured out how to get rid of the tachyon. They never got rid of the photon-like object. Why might they have liked to get rid of the photon-like object? The massless spin-1 particle. Why not? Well, why? It sounds like a good thing. It could be the photon. The reason was, at the time, string theory was not supposed to be a theory of photons. It was supposed to be a theory of hadrons, mesons, baryons, and there is no massless meson. There are no massless mesons. So this was thought to be a wart, not a feature at the time. People wanted to get rid of not only the tachyon, but also the massless photon-like object. In all the years that people have been doing string theory, the tachyon was very easy to get rid of, and nobody ever got rid of the spin-1 object, the photon. Yeah?
Is this the one they decided comes out of string theory, the graviton?
No, this is not the graviton yet. This so far is the photon. Or to call it the photon would be a little bit misleading. There are many sources of a photon-like object in string theory. Which one is the real photon and what do we do with all the others? Those are very model dependent. Those depend on details. To say that this is the photon would be misleading. It is a photon-like object. It is a gauge boson. It is a thing which behaves like a photon in many ways. And we'll need to come back to it, but I just show you this. Let's, shall we?
To summarize, right now, if you develop it, you have a m squared less than 0, which is the tachyon.
Yeah.
And that's not allowed.
Not allowed.
And we're not yet at the point where we
Well-
know how to get rid of it.
I wouldn't say so much. From a strictly theoretical point of view, quantum mechanics with an upside-down potential is perfectly good. There's nothing wrong with it. It just doesn't have a ground state, and that's bad. Yeah. So it doesn't look like the world. Now, of course, yeah, good enough. In this case here, we know what would happen to these guys. They would just turn over and I'll wind up oscillating about the bottom. Okay. Here, who knows if there's a bottom? Yeah. To get the gravitons, we have to study something new. The something new is closed strings. So far, these are open strings. Open strings means they have two ends. Ends, period. It's hard to have a string with one end, unless you're a Buddhist. Never mind. A Zen Buddhist. I apologize to any Zen Buddhists in the class.
It seems that you're looking at the properties of photons with polarization and the properties of these strings, and as far as that goes, it matches up.
Yeah.
So are there other properties of photons and other properties of strings that also match up?
Absolutely. Absolutely. Yeah. The interesting questions would have to do with the radiation of photons. Now, to have a radiation of photons, you have to have objects which carry charge. We haven't yet discussed what kind of objects might correspond to the things which carry charge. But once, if we found string objects which played the role of charges, we could ask, if we knew the rules, and we're going to talk about the rules, we could ask about the rules of emission of photons by accelerated charges. And the answer is yes, we would find out that they behave exactly the same way that, that emission of photons from charged particles works. Definite rules, definite probability distributions, definite radiation patterns, and those patterns would be reproduced quite precisely. So, yeah. Okay, let's move on. I think I mentioned this last time, but I'll tell you anyway. The basic process of interaction that takes place. So far, we're talking about free strings. Free strings means an isolated string moving by itself, unaccompanied by any other, and doing nothing except propagating along some axis and doing its own internal wiggles. But its wiggles, the manifestations of its wiggles, are simply a discrete collection of energy levels and also angular momentum. String can move internally in many ways. For example, one of the ways it can move, remember, these strings, the mathematics of them is the mathematics of non-relativistic strings. One of the things a string can do is it can rotate about an axis. Rotate like a dumbbell about an axis, the centrifugal force being the thing which stretches it out. Okay? So this must be something that these relativistic strings can do. This means that they can have all sorts of angular momenta. Not just one unit of angular momentum or 2 units of angular momentum, but you can spin them up. But when you do, because we're doing quantum mechanics, each unit of angular momentum costs you an additional unit of energy.
Can you have pitch pole rotation?
Can you have what?
Pitch pole rotation?
What's a pitch pole rotation?
Like one of them stays pitched and the other,
No,
that's not possible?
no, they'll rotate about the center of mass. Right. Any system, when it's rotating, will rotate about its center of mass. So the question is, where's the center of mass? And if it's a nice straight string like this rotating about an axis, of course the center of mass would be at the center. So, of course, if you had something to anchor the end of the string to, then it could swing around that anchor. And there are anchors in string theory, but
Could it swing around the energy level of an atom?
can it?
Like the photons holding the electrons in the center of the atom, can it pitch pole out from that?
You're asking whether an electron can circulate around a nucleus. The electron circulates around a nucleus. The reason that the electron circulates around the nucleus with the nucleus standing still is because the nucleus is very heavy. So the center, really, strictly speaking, they both rotate about a common center of mass. But because the nucleus is a couple of thousand times heavier than the electron, it looks like the nucleus is not moving. Okay. What did you call this? Pitch pole?
Pitch pole,
Pitch poling.
where you hold this end fixed and this end rotates and gets thrown out. It's like the Scottish do with the big logs of pitch pole.
Oh, yes. No, I don't know. I thought it was the Jews who invented that. Ah, the Russians. Yes. Okay. The basic process of interaction that allows strings to talk to each other, to interact with each other, to do things. I think I discussed this last time, but I'll tell you what it is. We're not going to do anything mathematical with it tonight. We will try to describe this a little bit mathematically later, but just qualitatively. The things that happen, particularly to these open strings, is very simple. It's really the only process. Everything is built out of it. And we're going to find even a simpler description, but at the moment, this is very simple. The only thing that happens, apart from these strings wiggling and doing their own thing, the only thing that allows them to talk to each other is that when endpoints find themselves at coincident points in space, in other words, when they touch, there is a probability, or let's call it an amplitude, for them to join. That's called a joining interaction. So there is some probability. They don't inevitably do it. There is a constant in the theory. It's called the string coupling constant. And what it does is it takes a pair of strings. Here's a pair of strings moving along in space-time. Upward is time. There's a string. Here comes another string. Their endpoints meet at this point, and they join together to form a single string. That's the analog in string theory of what in quantum field theory is the vertex, where two particles come together and join and make a third particle. This could be an electron and a photon, or it could be any of the other interactions that we've studied. Two particles come together, join, and make a third particle. Two strings come together and join and make a third string. But the process is very simple. It doesn't just happen any old way. It happens by the endpoints coming together, touching, and combining to form a single string. Now, anything that can happen in quantum mechanics can unhappen, meaning to say that quantum mechanics is a reversible theory. Anything that can happen in time in one direction can happen the opposite way in time. So that means that there is also an amplitude for a single string to break and form ends. If that probability were large, the string would have very little integrity. It would constantly be breaking up. If that probability is very small, then the string might last a long time and before it breaks up like that. So one of the assumptions in string theory is that this probability is small. The probability is called the string coupling constant. I think I said that. And it's the analog of the constant of nature, which would be, what would it be for the electron photon? It would be the electric charge, it would be the fine structure constant, right? It would be the square of the electric charge, that probability. Probabilities are squares of amplitudes. So the probability for two strings to join is like the electric charge. Right? But it's the same, it's quite independent of which kinds of strings are joining, in the sense that they could be the excited strings, they could be the rotating strings, they could be the vibrating strings. There's some probability when two endpoints touch each other that they fuse. And that same probability, that if the string is just moving along, minding its own business, that what's the opposite of fuse? Fish. Right. It can fuse or it can fish. Break. Break anywhere along its length. And those are... All right, so this is the basic structure. But one of the things that can happen is, just like a snake which encounters its own tail and is too stupid to know that it's found its own tail, might bite its own tail. The same thing can happen with strings. They're also rather stupid. And if the string happens to come around like that, in the course of its evolution, it might just do that. And when it does, the head detects a tail, and guess what happens? They join. So it's inevitable. There is no way around it that if you have a theory of open strings, and those open strings interact, in other words, have this joining and splitting process happening, then it is quite inevitable that the same theory has to have closed strings. Closed strings are unavoidable. Can you have a theory with closed? We're going to work out the mathematics of closed strings. I don't think we're going to do it tonight. We'll work out the mathematics of closed strings is very similar to open strings. We'll work it out. Question?
When you have these fission and fusion
Yeah.
situations, does that change the energy state of the string?
Yeah. Yes, it does.
Does the theory say how?
Yes, absolutely, it does. But for our purposes now, I just wanted to motivate for you why closed strings are inevitable in a theory of strings, or in a theory of interacting strings. Now, what about a theory of closed strings that ab initio starts with closed strings? Is it inevitable that there will always be open strings? No. No.
I mean, I agree. It doesn't make sense to me that there would have to be.
Doesn't make sense that there would have to be. But then you can ask, all right, but then how do closed strings interact with each other? If they don't interact by splitting and then touching other strings, and the way they interact is different. They interact, here's two closed strings, and they come together and then fuse to form another closed string. At no point did they ever form open strings. They came together like this, touched, and formed another closed string. So the answer is, it is quite possible to have theories of pure closed strings with no open strings, but it is not possible to have a theory of open strings without closed strings. That's interesting. It means that a prediction of string theory is that there are closed strings. It is not a prediction of string theory that there will exist open strings. It is a prediction of string theory that there must exist closed strings. just because there can be open string theories, no. There can be closed string theories without open strings. What do you think if the open string, if the interesting low excitation of an open string is a photon, what do you think the interesting excitation, lowest excitation of a closed string is? Also, the graviton. The graviton. And so one of the things that string theory literally predicts, because you can't not have it, is gravity. There are many, many string theories that have things like electromagnetism, but some of them don't. But there is no string theory that doesn't have gravity. Every string theory necessarily has gravity, just because it will have, I never heard of a string theory that didn't have closed strings. You've got to have some kind of strings.
Why is a spin to closed string necessarily gravity?
Ah, well, that's what we're going to come to. Why was the open string necessarily photons? Well, we did some manipulations and found out it was the only interpretation. We'll do the same thing, exactly the same thing with closed strings. Exactly the same thing. I don't think we have time tonight.
Can an open string convert a closed string into an open one?
If, in some string theories, the rules involve the splitting and joining process, in those string theories, a closed string can become an open string. But there are also string theories that don't have this particular process of breaking like this.
Well, if they do have open strings, will that also be possible?
Which?
If you have a string theory that has both open and closed,
Right.
then can a closed one interact with an open one such that it becomes open?
Yeah, there's a number of ways that a closed string can interact with an open string, but the simplest is the following. Once you have closed strings, in fact, once you have them, this is even implicit in open string theory, you can have, the basic thing that can happen is two ends can touch and join, but there's something else that can happen. The other thing that can happen is two strings can touch at a point which is not an end, and then they can rearrange. All right. So let's see what we started with. We started with two strings. Did we start with two or one? Yeah, we started with two this way, and this became this. Again, it's the same process where two things come in touch and then rearrange. All right? That's a process that can happen in string theory. I will have to prove to you that it can happen. I'm telling you now. Okay, so let's see what happens if you have a closed and open string. If you have a closed and open string, the closed string, here's the closed string. The simplest thing that can happen is the closed string can come touch the open string, rearrange, and now what has it formed? One big open string. Okay, so let's think about what that means. That means an open string is moving along to begin with. Let's draw it. Here's our open string. A closed string comes along, closed. And what's left over at the end? Open. That process will turn into the absorption of a graviton by a particle which is not a graviton. All right. So here's something we found out. Closed strings can absorb gravitons. Same way. Open strings can absorb gravitons. In fact, everything can absorb a graviton. That in string theory is why everything gravitates. In essence, and in a simple-minded way, the fact that an open string or a closed string can always absorb a graviton by this process is the is one of the ways of thinking about the universality of gravitation.
Do we ever get interlocking
What's that?
closed loops? Do we ever get interlocking closed loops?
Say it again. Oh, yeah, well, okay, we should talk about that. In weakly coupled string theory, where the interaction is weak, the strings are transparent to each other. But they can do this, but with a small probability. With a small probability, they come along and they do that. But they can also pass right through each other. So these strings are not obstacles like shoelaces that they can't pass through each other. They can pass through. Yeah, they can pass through each other. I'll bring you a superstring next time, and I'll show you how it works. Remind me, somebody send me an email to bring a superstring in, and I'll show you what it can do.
So you already have.
No, I'll bring you a real one.
So you said the joining amplitude was kind of independent of the state of the string?
Yeah.
And just, I mean, if I had something spinning really fast, then you might anticipate that it has a higher probability of fission. Is that just a choice in the theory, or is there some reason why that doesn't work?
No. The basic probability per unit time, if they're touching, to interact is the same for all strings. But keep in mind, if they're moving fast, they spend less time near each other. So if the probability per unit time is the same, if they're moving past each other fast, there will be less of a probability of them joining. Right? So it's basically a probability per unit time that's,
When you're showing these strings, you got smaller ones, you got bigger ones, right? Is there a fundamental characteristic of like mass or energy or something that represents that length?
Okay, so the first thing we should take up next time is units. I think that's what you're asking me about. Is there a unit? Right. Now there must be a unit because I've done all sorts of equations which didn't really make dimensional sense. What is x? X is a length, right? So it must have units of length. What about a creation and annihilation operator? Well, they have commutation relations. A dagger is equal to 1. So what's the dimension of A? No units. So how can X be proportional to A? There's some missing units in the story. Frequencies. What's the units of frequencies? Inverse time. But my frequencies are integers. Integers don't have any units. There's some missing units that I haven't put in here. And I think the first thing we want to talk about next time is units. What units? Another way to ask the question is, I tell you that adding an excitation of energy increases the mass or the mass squared by a certain amount. In what units? Mass, that's what we were saying before. In what units? In kilograms, in giga-electron volts, in slugs. What unit does 1 unit of excitation, how much does it increase the mass by? What answer would you guess?
Planck's mass? No, that's too big.
In a fundamental theory of gravity, you might think it's the Planck mass. You might.
It's too big. That's too big, though.
It is too big, yeah. So we're going to find it's a little smaller than the Planck mass, but that's something. Next time we will take up explicitly the issue of units, and which is clearly important. It's important, yeah.
With Planck theory, is coupling constant the same, or can strings have different ends and different probability of joining?
In the simplest string theory, it's just a single constant. And generally, it's a single constant. Yeah. In fact, really, strictly speaking, there are no constants in string theory, but we'll get to that.
Before we beat this sex of strings to death,
there's the open and there's the closed, is the possibility of a string splitting on its own,
Splitting means breaking.
Lengthwise.
but not separating,
Oh, it means.
like a Y. Like a Y, like single splitting, but not
Split
splitting.
lengthwise.
I think I know it, lengthwise. No. No, that is not,
You're not allowed to split hairs.
you're not, you're not allowed to split hairs, right, right.
Join an edge to a midpoint?
I think you're asking whether you can have a more complicated object like this. Now, this doesn't correspond to a Feynman diagram. It corresponds to three strings joined at a vertex at the center. Is that what you're asking? Yeah, there are string theories that do have that possibility. There's an enormous variety of different string theories. The question is, what do they all have in common? If you ask, what is the generic prediction of string theory, then you're really asking, what do they all have in common? And the only thing that I can really think of that they all have in common is they all have closed strings and they all have gravitons. Some versions have open strings. Other versions have, I call this a bolo. You know what a bolo is? Argentinian cowboy swings it around and entangles his feet in it and falls over and falls on his face. And, right. Yeah. In fact, in hadron physics, remember, hadron physics is a version of string theory. When we talk about units next time, I will tell you the difference between string theory but in the theory of hadrons, do you know what this kind of thing would be? Versus this kind of thing?
Quark, could it? 3 quarks and a proton.
It'd be 3 quarks. Baryon. This would be a quark and an antiquark. Right. So yes, string theories can have these kind of things, but the one thing they always have is the closed strings.
Do the coupling constants change depending on the dimension of interaction for the strings as well?
I'm not sure what the question is. The coupling?
If the strings are colliding in one dimension,
Oh.
like Blackwater, and then we have another dimension, the string coupling constants will change as well.
Yes. Yes. There is a dimensional, by dimensional I mean the number of dimensions of space. There is a story about the values of the coupling constants as a function of dimensions. Yes, there is, but we'll take that as we come to it. One more question. I want to go home, but yeah.
I missed the first 15 minutes, so you may have already answered it, but when they're moving and they combine and break, what is is it the gravity that is making them move? Or
No.
Charge or?
No, think Newton for a minute. Is it gravity that makes things move? No, it's inertia that makes things move. Once they start moving, it was Aristotle who said there has to be a cause for motion. It was Newton who said, nonsense, things, if you set them in motion, will keep moving. Strings are the same. It's not gravity which makes things move. What does gravity do? Gravity causes things to accelerate. So we haven't gotten to gravity yet, and where gravity comes from. So far, this is a theory which we have no particular reason up till now to have any gravity in it. What makes things move in general?
Forces and mass accelerations and
Force.
Newton's laws.
Interaction.
Curved space.
Inertia keeps them moving. What starts them moving?
Well, the kinetic energy.
An exchange of momentum with another particle.
Possibly.
Something in nature of time?
I think you have to think about that. Supposing something weren't moving. Now you look at it from another frame of reference, it is moving. So what made it move?
Changing your point of reference.
Changing your point of reference.
Well, if you have a system, you have the energy of the whole system, which is divided among the particles.
But all I'm telling you is, even if a thing is not moving in one frame of reference, it is moving in another frame of reference.
Well, that's,
So even Galileo understood that. So Galileo knew enough not to ask the question, what causes motion, but to ask the question, what causes changes of motion? And that's forces. Forces cause changes of motion. So,
Quantum fluctuating?
well, in classical mechanics, forces cause change of motion. Right? What causes the motion in the first place? Well, initial conditions. Initial conditions. What caused the initial conditions? Woody Allen.
For more, please visit us at stanford.edu.